Good morning, everyone. I'm delighted to have with us today Professor Stephanie G. Paal. She is going to talk about scarce data approaches to transfer knowledge across disparate domains, a study in extrapolation via machine learning. Dr. Paal is the Williams Brothers Construction Company Associate Professor in the Zachary Department of Civil and Environmental Engineering at Texas A&M. She joined the faculty at Texas A&M in the fall of 2016 after completing a postdoc at EPFL. We just talked about that. She received her master's and doctoral degrees in civil engineering from Georgia Tech in 2011 and 2013, respectively. Additionally, she received a BS in architectural engineering from the University of Texas at Austin in 2009. Dr. Paal has extensive background knowledge and expertise in machine learning, machine vision, and the applications of these technologies in infrastructure and structural condition assessments and other infrastructure-related practices. Her research focuses on mitigating the effects of natural disasters on our built infrastructure by integrating traditional civil engineering practices with emerging techniques and technologies. She's won a number of awards, honors, etc. I cannot take any more time to go on and describe them. But we're really happy to have Dr. Paal with us. So thank you for doing this, and it's all yours.
Thank you, Prannoy. All right. So thank you guys for having me here remotely. I am going to talk a little bit about just kind of like a couple of examples as to how we use machine learning to understand behavior, mechanisms, et cetera, when we don't have access to large data sets, and why that matters. So I think in this room or this virtual room and just in the world now, everything on this page is very common now, right? We're all kind of thinking about machine learning every day. If you're not, hit me up. I'll explain to you why we should, if this presentation doesn't do it justice. But these things are just kind of like general terminology, what's going on with machine learning. But when you think about machine learning and why it's come so far, and it's kind of integrated in everything, is because when you compare machine learning to the more traditional approaches, and let's just think about civil, environmental, architectural engineering, the space that we're all most likely from, right? What you get with machine learning in comparison to those traditional approaches is increased accuracy, computational efficiency, which oftentimes lends towards a tendency for real time, right? So when you're working with your Claude or your Genesis or, Gemini or ChatGPT, whatever you're working with, you get responses right away. As well as generalization capabilities, the ability for these models to understand large sets of data and be able to kind of extend knowledge to many different, let's say, material types rather than just one material type. So being able to do all of those things is based on the fact that machine learning really benefits from large data, right? So these are all advantages because machine learning is is capable of like absorbing and understanding very, very large data sets. When we look at things in our group, though, we're trying to understand what happens if we don't have large data. So how do we predict performance? How do we understand structural mechanisms? How do we extend our understanding of materials or configurations or systems when we don't have a lot of data, right? So there are two main reasons why this is where we're living in my research group. So first off, when you think about new designs, new materials, new construction processes, take 3D printing that you see here. If we want to be able to design or understand or implement any of those things rapidly, then we need another approach, right? We can't just go in and physically test hundreds, if not thousands, to understand those designs, materials, or new construction processes. So we have a little available data there, right? In addition, and this is where most of my work stems from because I started out my PhD doing earthquake engineering. When we look at the changing climate, when we look at global warming, we see that there are new, more extreme loads, right? Whether that be in quantity or intensity, we are seeing that there are more frequent natural disasters, that there are more intense natural disasters. And in each of those things, we also have an increased intensity in terms of how they impact environment, society, infrastructure, right? So in each of these instances, if we want to be able to design for or operate infrastructure rapidly without actually waiting for many, many natural disasters to occur or testing many, many 3D printed structures. We need some way of predicting behavior, mechanisms, etc., with little available data, right? So again, we asked this question in our group, how do we predict performance when there is little available data? With that, we're moving from interpolation, which is a classic machine learning problem. Everything, I would say 99.99% of machine learning that's being done is an interpolation problem. We have a large amount of data and we're trying to fit the space in between. We move in my group from interpolation to extrapolation. With extrapolation in machine learning or any data-driven technique, you have a number of typical challenges. First off, we are unable to accurately represent the distribution of the data. We're unable to reflect the underlying patterns, which is the key benefit of machine learning. And essentially, that's because we are biasing our training sample. So when you think about supervised learning, you're using a large set of data to train your model. In that instance, if you're moving to extrapolation, you're training it on data that maybe has like earthquake magnitude of 1 to 7. And now we want to be able to predict for that off chance magnitude 8 earthquake. So our data is biased to the lower magnitude earthquakes. And that then causes a large bias in our model, which we all know won't represent good results. So there are two main techniques that we use in my group to be able to uh, develop models when there is little available data, as well as just like a hybrid physics machine learning approaches that I would argue in terms of machine learning are important no matter what you're doing. It's important in our world where we understand the mechanisms, the physics to kind of integrate that, whether it be to constrain our models or to enhance them in some way. But in this presentation, I'm going to talk about all three of these things. So transfer learning and few shot learning are the two main techniques that we use. They're pretty similar. I'll talk about a little bit of their differences, but how we use both of these different machine learning techniques in order to do extrapolation within the civil engineering or mostly structural engineering space. So for this 40-minute time frame or what I have, I'm going to talk about three different examples and the applications of transfer learning and few shot learning in those examples. So just for the sake of me being a civil engineer, I'm going to go from the material to the structure level, right? So we'll do a material level example where we're talking about the most simple thing that hopefully all of you did in your undergrad time, predict the compressive strength of concrete mix designs. Then moving on to the component level, we'll talk about the shear strength of concrete beams. And then structure level, we'll veer away from concrete and just talk about predicting wind pressures on low-rise buildings, something that hopefully is interesting to you guys in Miami. So at the material level, we're looking at using, like I said, two techniques in all of these different approaches. The first one being transfer learning. So in order to explain to you transfer learning, I'll talk about it in some pretty simple terms and then hopefully in kind of some broad terms that everyone can understand. What we're doing with this technique of transfer learning is we're just building a large relevant data set. Relevance is the most important. So this is where I make an argument for all of you in this virtual room to understand machine learning, to try to implement the different advanced techniques that are happening out there, because the only way that these models will be good is if we have some understanding of the domain in which they are being applied, right? So you have to understand the data that is being used for training in order to use the right algorithm and get the best out, the most out of these different tools. So relevance is the most important here. Once we build a large relevant data set, we're going to call that our source data set. Then what we do is we have the target data, which is what we're caring to predict for. So in this case, it's going to be some sort of different concrete mix. And we want to use just a little bit of that data because we're saying we do have a small amount of data. We don't have zero data. We have a small amount of data. Let's use a small amount of that data in conjunction with our source data set that is relevant to that small data set. And then we'll build a model based on the large data set, but it's going to weigh the target data points as very important. It can be in terms of actual weights. There's a chat. Do I need to read it?
No, no, it's for later.
Okay. So the weights could be technically weights in the system, in the algorithmic structure, or they could be something else. But essentially what we're doing here is we're hyperfixating on these target data points. Now that we understand the source data, we're trying to figure out what's different about these target data points and what's similar. And then through that, we'll be transferring the knowledge from the large data set to the small data set. So hopefully now we can talk about this in terms that everyone here understands. I teach structural dynamics, right? Structural dynamics, advanced structural dynamics. There's a reason why every class in in undergrad and grad school is a semester long class, right? Whereas you may have taken 5 years from kindergarten to fourth grade to understand basic math, right? So this garden math, this sports math, over here, we're just talking about basic math, addition, multiplication. It takes us a very long time as children to understand that. So we have lots and lots of repetitions. Then we move on to something like calculus, which maybe you do in 1 or 2 years, depending on what kind of school you went to. Maybe it even takes some students 3 years. From there, we have 1 semester of differential equations, 1 semester of structural dynamics, right? We're able to learn these later tasks. So, most importantly, let's talk about structural dynamics. We're able to learn it faster. It's our target because we have this large understanding, this source data set that is relevant to the target data set and allows us to expedite our understanding on the target data set. So moving back to the specific example of material level, how do we implement this understanding or this idea of transfer learning? We're looking at a number of different types of reasons. So the motivation for this work is, you may have a data set that's we want to reduce carbon emissions. We may be using some recycled aggregate. We may be using some other non-traditional inclusion. That's what we'll talk about today. Maybe you want a different property, a different behavior. Any one of those things could be why you might need a transfer learning model in this concrete space. So for us here, we're using just a basic set of concrete core samples. We have about 1,000 samples that are the large data set, and those are your basic concrete design, right? And then we have a small data set, which is about 77 samples that could be any new mix design for those 4 motivations on the previous slide, or in this case, we're just talking about non-traditional inclusion. So we're talking about some steel fiber reinforced concrete, some additional admixtures, and trying to understand really quickly how does the behavior or the compressive strength in this instance change based on those inclusions, right? So we do what I said before. We have this large data set, this small data set. We create our mixture data set where we're weighting those steel fiber reinforced concrete and additional mixture samples with more importance because we've already understood the large data set because we have so much data there, right? Then we can predict the performance on this new mix with very little information about this new mix. So here you can just kind of see what are the different features that we're using to predict for this instance. One thing that is interesting here is that this feature space is technically considered a heterogeneous feature space. And so you have a heterogeneous transfer learning problem. And that just means that the features in the source and the target are different. And so it does cause a couple of like hiccups or, just other things that you have to consider in terms of how you develop the model. Another reason why it's important that somebody who understands the domain is there developing the algorithm, right? If you had coded it as a homogeneous transfer learning problem, then it would just remove a lot of those features that you do need, right? We need anything about those fibers to be considered in this model because that's what makes the data set different. So here's what that looks like in terms of a heterogeneous transfer learning problem versus a homogeneous transfer learning problem. In the source domain, you would just see that there are some slightly different data points that are entirely different from in the target domain, you have some data points that are entirely different from your source domain. And in that's just, these features, I don't have a pointer, down on the right-hand side, mostly that have to do with the fiber, right? And then you have that removal of the blast furnace slag. So in this heterogeneous transfer learning problem, it is difficult to map across these two distinct feature spaces. And so we need a specific solution, right? So we knew that as the domain scientist, and now we're saying, how do we change our algorithm accordingly? And so we picked a specific algorithm that was able to handle that heterogeneous feature space, and that is called GEP, or genetic expression programming, where we're just able to change the combination of features, as well as you'll see it creates kind of a mathematical equation, and we can change those throughout the model's development. So the model that we've developed is called 2M2P, and it's just basically a modification of your basic genetic expression programming model. We have It's modified so that we can deal with this heterogeneous transfer learning problem, as well as we want to be able to create very interpretable models. So this is a question or a concern that will be brought up over and over and over again if you do machine learning within the civil, environmental, architectural, engineering space, right? We use these models ideally in the end for real problems. And so if you give this to somebody who did not build the model, does not have an intense understanding of computer science, of machine learning, of anything really but the data, then we need to have some way of interpreting or explaining that model. I mean, this is probably a question that's up for debate considering the current state of large language models and agentic reasoning and whatnot. But my argument would be that we should try to create interpretable models so that the people that are using them have at least some understanding of the underlying mechanisms. And so that's the point here. You might see this equation and think that's not very interpretable, but at the end of the day, it is in comparison to some sort of black box model that just outputs what is your FC prime, right? So in this case, you can see a number of the different features that are in there. You can see kind of how they're weighted, how many times they show up, et cetera. And then you could back calculate this with a simple Excel spreadsheet and just kind of understand what's going on. And so that is one of the benefits of using a GEP model is you can constrain this equation however you want. You can modify it to get a reduction in accuracy, but in more simplified equation. You can use, like we've stuck to just like addition, multiplication, division, subtraction, as you see here, but you could also, abstract it a little bit more and use square roots or, powers. And this is just the equation that we've simply provided here, right? So you can see in terms of the results, the 2M2P model, which is our model, in comparison to just using your source data set and just using the small data set, right? So that's the baseline model. And so we expect that to be bad, right? So we're saying if we only had 77 data points, then we would only be, and we were going to build a basic machine learning model, we'd only get an R squared value of 0.42. So it's not great prediction. You want an R squared value around 1. You can see that like the best setup is that 0.868. Let's see, I can probably, no, pointer. You can see there is a good scenario, right? Because we randomly do this 10 times. And in some instances, you have the right set of data as your training data. But in order for you to have a robust prediction, you can see that the 2M2P model gets you much better performance, right? We also compared this to some traditional machine learning models to show that the performance is much better than like your support vector machine or your random forest in terms of all the metrics, right? So moving on from this compressive strength problem, we can see how we could apply transfer learning a little bit more. So in this example, I'm going to go a little bit more expansive. And what I'm asking here to some extent is how far can we stretch this problem of extrapolation? So before we're just moving to a concrete core sample that's slightly different. In this case, we're going to look at 3 different experiments. We're going to look at these reinforced concrete beams, and we're going to say, is it possible to transfer knowledge across various feature spaces? So the 3 that I'm going to show you here today is we're going to transfer across failure mode. So like a shear critical or a flexure critical beam. We're going to transfer across a loading type. So how the loads are applied to the beam. There are many different tests. We're going to split on that. And then compressive strength. So just one of the concrete material properties, right? Splitting on that and saying, can we predict from low to high compressive strength beams or high to low, vice versa. In this data set, we have about 2,000 specimens. So they're from 1948 to 2007. This is just when the data set was kind of, people stopped testing most of these specimens because we had already tested 2,000. But also the data that is available publicly. In this data set, there are both rectangular and T-beams. There are no stirrups in any of the specimens, and it's primarily normal strength concrete without any pre-stressing. So we are, oftentimes I get asked, that's not a very big data set. One, we care about small data, but just in terms of like the source data set needs to still be large. We constrain our problems, right? In civil engineering in general, for the most part, all of our problems are constrained to like a material type or a component type, or in this case, a specific type of a component with a specific type of material properties. So here you can see, again, just the different parameters or features that we use, as well as their statistical description. So we're just looking at section and material properties, as well as the load, right? That's all that we really care about here. And then from there, can we predict what the ultimate capacity is of this component? And so again, I said we split on three different things to explain those. Specifically, we're talking about mode split. We're going to use beams that fail in shear, which is a much larger set of this data set, to beams that failed in flexure. And that makes sense based on the fact that there is no shear reinforcement. Then we're also going to look at this load type split, which is, I'll show you a picture of what each of those load types look like, but we're taking the largest set of data, which is called load type P, and trying to predict load types U1 and U2 based on that data set. And then the compressive strength split, we're splitting at 87 megapascals just to get a large set of data that has some higher strength, yes, higher strength relative, and then the below 87 megapascals, predicting for those as the target. So you can see here for the load split, we can see similar plots to what we saw before. We can also see a similar equation. Here you're seeing the ultimate shear capacity of the beam. And you can see here, in this equation, like I said before, you're able to do multiplication, addition, subtraction, and division, but we also allowed powers to a small degree, right? So you can see one term is to the second degree. We looked at this in comparison to existing design specifications. So this is ACI as well as CSA, the Canadian standards. And then you can look at it in terms of the three different splits that we considered and how well the model, same model, 2M, 2P, performs. In the plot on the right, you can see all three of them. We're looking here, at like just focus on the mode split, right? So you can see with the green, that's your transfer 2M, 2P model, it performs drastically better. Obviously, the source doesn't work. So beams that fail in flexure are drastically different than beams that fail in shear. So if you create a model that is designed to understand beams that fail in shear, and then try to use that just to predict for beams that fail in flexure, it will not work. It is negative r squared 9 times out of 10, as you can see there. And so you're going to get a model that you might as well just draw a straight line, right? Same thing for the small data set. We only have 153 specimens that fail in flexure. So you can see the maroon line on the first set of curves. It doesn't get above a 0.25, 0.3 if you're looking at the extremes. But then your green is your transfer learning model. And with that, we have a really low standard deviation, as well as an average of 0.75 r squared. So most of the time, we're getting pretty good prediction on those beams that fail in flexure without using many of those beams. Here now is the load split problem, the load type split problem. And so we have about 1,700 beams that are like that first one. So a simply supported beam with a concentrated load right at the center. And then the other two ways to kind of simulate that are what's looking like a distributed load for your support and then a concentrated load at the center or at the center, or a distributed load for the support and then that concentrated load split evenly to either end node, right? So we could see how these are somewhat similar, which is why, the small data set here, you're looking at the middle three plots, it's pretty close there, right? So we have enough data to be able to provide a pretty good predictive model. The transfer learning helps, so getting more of that data is helpful, but it's just not as complex of a problem. Is what we're seeing here. You can also see the comparison of the equation that again is not beautiful, but it does give you some sort of understanding of what the different features are, how they interact with the ultimate capacity, the ultimate shear, right? As well as the comparison between this machine learning model and ACI or CSA equations. Finally, we look at the compressive strength split, and this one isn't a great performance. Obviously, it's better than if we just use the source data set, but what we're seeing here is that 56 beams with a low compressive strength or compressive strength below 87 megapascals, just that small data set is able to perform, for the most part, better than our transfer learning model. And so this, gives us the argument that we would probably need to do more. We need to understand this better. You can still see like the best case scenario is better. So if we were able to choose which experiments to do to try to get most of that feature space represented within the small set of target data, then we'd probably be fine. We have much better performance than ACI or CSA. We have this interpretable equation that, albeit again, not beautiful, does give us some understanding of what features are interacting what. And then we're able to get a very good prediction in terms of, at least one run. So if we were to identify which data points are the most important to test in the future in this sort of scenario, then we'd be able to get pretty robustly good predictions. So here is what is kind of most interesting to my group is if we have a reduction in data availability. So all the results you saw before, I think were like for maybe the worst case scenario of 5% data availability or something like that. We're saying as we reduce or going from left to right, increase our data availability, how does this model behave? And you can see in all times, this 2M2P model, the transfer learning model, is the most stable, right? So you're keeping pretty high performance regardless of the data availability. And obviously, it grossly outperforms your source model, which is just using whatever large data set you have. And it grossly outperforms, I mean, not grossly, but in the most extreme case of 5% data availability, it obviously outperforms pretty substantially, 60% better than your baseline. So just using a very, very small data set. So the place, like the location where these models are the most important is where you have really, really small available data, which is again our motivation, right? So to sum up the transfer learning part, we see that we can use it to robustly and accurately predict for these out of sample scenarios. So looking at it as a solution to extrapolation. But really what I think is most important about some of these examples, albeit again, the equations are not beautiful. They're definitely not simple. We do see that if you take a little extra care, if you focus a little more, you can provide something that is interpretable. It is important that, us as engineers, we are able to identify what those features mean and how they interact with the ultimate shear capacity, especially if this refers some new material or new set of designs, right? And so it is useful in that way and would be useful for practitioners. But now moving on to the final example, which if you're from the concrete world, I'm sorry, we will take a detour into the wind world, which these are just kind of like little plastic experiments. So they represent low-rise residential infrastructure, mostly wood frame. But what we're asking in this example is that question of, if you look back here, I said the most improvement is at the 5% data availability. So when we have the least available data, we see the most need for these types of approaches. So the question is, what if the available data is even smaller, right? What if we have 1, 2, 3, 4, 5 data points? Eventually, we want to ask, and we're focusing now on what if we have 0 data for this new space? Can we build a model that's able to predict in that way? So in this case, I bring you this idea of few-shot learning, okay? And I know I can't like access the chat right now in the mode I'm in, and I know you're probably not all going to speak up, but I would like you guys to look at these 4 images here and to ask, you see 2 pictures of a lynx, you see 2 pictures of a Pallas cat. And now you have this new image. This new image you want to figure out, is it a lynx or a Pallas cat? Right? So everyone take a look and then think about it. My guess is that 100% of the room right now, or the virtual room, would say that this is a lynx, right? We can pretty quickly deduce the ear shape is different, the pattern on the fur is a little bit more like the lynx than it is the Pallas cat. So if it's one or the other, we're going to say it's a lynx, right? So before today, I mean, I've seen these images before, but my guess is before today, if you haven't seen my slides, you've never seen really 4 images of lynx and Pallas cats. And so this is 2 samples of each instance, and we as humans are able to deduce really quickly what is this new image, right? So that is the concept of few-shot learning. We as humans learn so quickly with just a couple of samples if we're given the right distinctive samples. And so we're going to do the same thing with any structural engineering application, but just in terms of this algorithm. We're going to look at two different data sets. We're going to quickly, with a couple of different data points, we're going to create this meta training set. So you see over on the right-hand side, the four triangles that are separate from the yellow circles. So in traditional machine learning, we would just look at everything together. Now we're going to, again, in a slightly different way, hyperfixate on these four samples or 10 samples or two samples. From that, we build what's called the meta learning algorithm. That's the few shot learning algorithm, and test it on the remaining held out meta testing set. So more of those blue triangles. So we looked at this in terms of wind engineering in many, many extrapolation cases. So we have a large set of data from experiments that have been done, and I'll show those data sets in a minute, all over the world. And through that, we wanted to solve a couple of different problems. We wanted to look at, can we extrapolate across roof types, so the gable versus flat? Can we extrapolate from the wall to the soffit? Um, that pressure difference right there is not well understood, and it's often inaccurately calculated according to current design standards. And then also the scale problem is a very interesting problem. So we wanted to be able to extrapolate from small scale to full scale. We'll talk about that. And then isolated versus clustered. It's much easier to do an isolated test in the lab than it is a clustered test. So if we could just extrapolate from the isolated to clustered scenario, then that would make experimental testing more efficient, as well as just be able to be done more often. So we're going to look today just at one example for the sake of time. I know I talk fast, but I don't talk that fast. Um, so we're going to look at this case of small scale versus full scale structures. This is a really interesting problem. So you can see here, this is just a number of different tests. This figure is from the Wall of Wind facility in Miami, just down the street, right? And so what you can see here is the full scale. So the red circles and the green dots are the large scale and the full scale specimens. And the small scale structures all kind of follow the same trend, right? And this is pressure coefficient. So this is right here, you see the minimum pressure coefficient. We'll look at peak, min, standard deviation, I think, today. So the trend is pretty good for the small scale, but when you get to the 1 to 6, when you get to the full scale, that trend degrades, right? So the difference to some extent can be greater than 50% between the scaled wind tunnel tests and the full scale measurements, especially for the extreme cases, which in my world, I come from natural hazards engineering. I think just regardless, that's what we care about, right? Like we as engineers design for worst case scenario. We do not want uplift at the corners of a roof when a hurricane comes through, right? We want our roofs to stay on our structures. So in those extreme cases, we actually have the greatest disconnect between the scaled wind tunnel tests and the full scale measurements. And that's because it's hard to simulate a high enough Reynolds number. So this is to do with the flow. This has to do with the mechanics that are going on in this wind engineering problem. So we can't neglect the scale effects in these small scale models. So I said we'd talk about the data. So we use a lot of data throughout all of these different experiments, but in terms of the scale data, what we're looking at is data from the Wall of Wind facility down the road, right? And what they did is there's a flat roof structure out at Texas Tech University in Lubbock. And it's a very simple structure. It's been instrumented, and so we know how it's performed under a number of different events. And they simulated that built that to scale at a number of different scales. We also look at other data. So in terms of, we consider a lot of data in building up this model. So there is also some data from NIST, the National Institute of Standards and Technology, as well as Tokyo Polytechnic University that can be used in conjunction, which is a number of different scales, a number of different room types, a number of different plan dimensions, etc. You can see here, again, these are some of the input variables or the features that we use in our model. This is the basic, rectangular roof. We're just looking at roof pressures is what we're trying to predict. And so we need the X and Y coordinates of different roof pressures. We need the scale of the structure. We need the wind direction. We need the turbulence intensity and the wind speed. And then we're going to output the different roof pressures. So here you can see we had over 11,000 data points for the roof area that come from the Wall of Wind data set at the different smaller model scales, right? So the goal is to be able to extrapolate to the full scale specimens. So we're using from 1 to 100 to 1 to 6. And then we're using just a very small number of data points from the true Texas Tech University full-scale data set. So 48 data points in comparison to your 11,404 data points. So the 48 are your target, or your, in this case, your meta training set, right? And then we test on the remaining large number of data points for the roof area of the Texas Tech University full-scale structure. So that's about 1,950 data points. You can see here, um, we have your CP mean, so the mean of all of those roof pressures for each individual run, as well as the standard deviation of the roof pressures. And you can see the mean squared error and the R squared of each of those predictions. What I like to note here is how imperfect this is and how unfortunate it is, right? So, um, if you look at the data, it looks like a good fit. If you're just a general machine learning researcher, you're going to publish these data sets, I mean, these results, and be so proud. You walk in and talk to a wind engineer, they're going to say, excuse me, what we care about is that negative 3.5 value, right? So if you're looking at the green plot, we have these extreme values. The extreme wind pressures are what we care about the most. Same thing is true for the standard deviation. The highest standard deviations are the ones that we actually really need to get most accurate. So what we need to do is we need to bring this entire plot in, right? And so let's try this again. Here we have 4 more pictures. We have 2 jaguars. We have 2 leopards. We look over here and we say, is this a jaguar or a leopard? I'm gonna give you guys like 20 seconds. Think about it. Look at them. Can you tell what are the differences? How do we figure out what this is going on here? And normally, if I were to do this in a room full of people and I have you raise your hands, it'd probably be about like a 50-50. Is it a jaguar or a leopard? Okay. So we're not sure. This is a more complex problem, right? And so now I give you some prior knowledge. I say jaguars have rosettes with these inner spots. Leopards do not, right? And so what is this? Is this a jaguar or a leopard? At this point, we'll probably get 100% accuracy, right? So this is, in fact, no, I don't show you, I don't tell you, but it's a leopard, right? It doesn't have those inner spots. And so now we get from 50% accuracy to 100% accuracy, hopefully, right? With this prior knowledge. So let's do the same thing in the wind engineering space. We're trying to predict for full scale performance based on small scale performance. So we need some prior knowledge. We already understand, and it's in the AC design specifications, that there are these different zones of the roof, which I'll show you in a second, that have different wind pressures. And so what we're going to do is we're going to look at these different zones, and we're going to group all of our data accordingly. We're going to build kind of like a hierarchical or clustering model. And so if for zone 3, we really only understand zone 3. For zone 2, we're using all the data for zone 2 and 1 accordingly, right? So this is all adopted from ASC 722. This is for flat roof structures or structures that have a slope of 7 degrees or less, which is our structure. So us as engineers understand where to go look for this, right? Where to look for the prior knowledge to enhance our model. So here you can see we took this into the algorithmic structure. We split it into really 6 zones. So zone 1, zone 2, and then zone 3, each corner. We really needed to focus on separately because the wind direction really matters. And those are most extreme when the wind direction is at that zone, right? And so what we did is we updated our meta training set to just have data points from each of those different zones and hyperfixate on those accordingly, right? Or respectively. So then the few shot learning model is now done kind of 6 times and clustered together. So you can see here on the left in orange, you see my previous results, right? Where at the extremes, we have a little bit of dispersion. It's not quite as accurate. And then on the right-hand side, although you're not seeing like a drastic improvement in terms of your R squared or your MSE values, you see it where it matters, right? So in the most extreme values for your mean CP on that top right-hand green plot, you see a much closer alignment along that red line. And same for the standard deviation, we are bringing it in to some extent, right? So we're improving to some extent each of these spaces where it matters most for our applications. So, in conclusion, and I'm sure I spoke quite fast, but what we see with all of these different case studies is that with the right amount and the right type of data, extrapolation is possible, right? I think, as we look at being able to understand data points that we have very little information for, there is not currently an approach to do that, right? Historically, what we've done is physical testing in an experimental facility. If we don't have the time or the money to do that, which I think with this age of AI rapidly increasing, we're going to have much less time to do that, but we also have access to more and more data. So figuring out what's the right amount, what's the right type of data, then we can actually do some sort of extrapolation under some sort of robust scenarios. I'd also just like to argue, which I did a tiny bit in this presentation, but I will argue till the day that I die, that hybridizing machine learning and physics-based knowledge is really necessary to address these problems, especially the more challenging ones. So we saw that in terms of using an equation to kind of understand what's going on, but mostly we saw that in terms of the prior knowledge in that last example, right? So understanding that those zones are different. If you don't tell the machine learning model that these zones behave, that wind behaves differently in these zones, it doesn't necessarily know that, right? And we want it to know that. So it may learn it over time, but if you don't have enough data, it's important to use some hybridization of machine learning and physics-based knowledge from the get-go. Um, in addition, talking about the first example, and the second example, right? I just think there's a need to provide enhanced and more interpretable solutions, especially for extreme scenarios, especially in instances where you don't have a lot of data. We want to be able to trust these techniques. And so, how do we do that if we just look at it in terms of a black box? There are many, many ways to look at interpretability or explainability. I showed one example today in terms of using an equation, but there are many, many, many more ways, and I'm happy to talk with anyone about those if desired. But in general, just my takeaway for any presentation that I give that has anything to do with machine learning, which is 100% of my presentations, is it's important to use machine learning to understand more, not to understand less. I hope that any of you that are implementing machine learning in your daily lives or in your research workflows are using it to help you understand more, rather than to understand less. Most of the more traditional applications have been, let's make something 0.2 seconds faster. Let's get this out there now. Let's, kind of abstract things by now we can handle all of this data. But if we're abstracting and kind of obfuscating what's going on, then at the end of the day, you can't tell when mistakes are being made. And also, what is the value, right? So, as domain scientists, I think we have the opportunity to use these tools and techniques to better understand the behavior of our structures, the impact on infrastructure, etc. So, that's my last token of, I don't know, advice. And I'll leave you with that. Obviously, I'd like to thank, the funding agencies, so the National Science Foundation and American Concrete Institute, as well as the students who I couldn't do this without. So, thank you guys.